We're going to start out by standardizing our Acumet pH meter. So we're already in pH mode, so we can skip over the first direction here. We next need to click the setup key twice. We're now press enter to clear the original buffer. So we're ready to start. So the first thing we do is rinse this electrode. So right now this electrode is covered up. There's a solution inside this plastic stabilizing this electrode. We need to rinse the electrode with distilled water. So this is going to be my waste beaker. So I'm going to basically rinse and clean this with distilled water. And now we need to immerse this in our pH 4 buffer solution. So I'm going to have pH 4 written here. I'm going to put my pH 4 buffer solution in this beaker. And I'm going to go ahead and immerse this down into the pH 4 buffer solution. And press standard again. Once the pH stabilizes, I'm going to press standard again. It recognized that it's a pH 4 solution, so now it has returned to the measure screen. So I'm going to take this out of here. So again, this is my pH 4 solution. I'm going to rinse this with some water. Alright, so now we're going to go ahead and add our pH 7 buffer. And make sure that reads accurately. And I'm going to re-standardize it in pH 7, so I have to standardize it twice. So standard, it says standardize, press standard again. Alright, so right now we have our pH meter in a pH 7 solution. It's reading very close to pH 7, so that's good. We can take this out. Again, this is I have this labeled buffer on a beaker, but we can take this out and check it with the 1 molar hydrochloric acid solution. So we should see the pH drop to a very low number. So it looks like we're at negative 1.62. So that's good. I'm going to rinse this off now. And then double check our sodium hydroxide solution. So this should read a pretty high number, around 12 to 14. And it does, so that's good. So our range seems reasonable for our pH meter at this point. So we're going to rinse that off and then just put it actually back in our pH 7 buffer solution. As we go ahead and set up the rest of the experiment. Alright, so for this we need to weigh out 0.2 grams or 200 milligrams of glycine. And again, that can be a ballpark number. We just need to make sure we record exactly how much we have. So I'm going to zero this. So we're adding glycine, so that gave us 23 milligrams. We need about 10 times that amount. And now we have 196.8 milligrams of glycine. that should be good to go ahead and run our first titration. So let's just double check that number. So 196.7 milligrams of glycine. Alright, for the experiment with glycine, we are actually going to use a 25 milliliter volumetric flask. So I'm going to go ahead and put my 196.7 milligrams of glycine in here. And I'm going to go ahead and just run water down here to make sure we transfer everything. Alright, so our whey boat is cleaned out. We definitely transferred everything in there. Now we're going to add about 15 milliliters. Hopefully most of this dissolves. And then we are going to add our hydrochloric acid to make sure this starts out acidic. And I'm just going to stir it in with this pipette. Everything's dissolved. That looks pretty close. So now we need to add our hydrochloric acid here. I'm going to add about 3 milliliters here. And then I'll fill the rest with distilled water to get to 25 milliliters. Now the bottom of our meniscus needs to be right on the line of this, so it looks like we need about one more drop. And now we have exactly 25 milliliters. So I'm going to transfer this to this beaker, and we're going to test to make sure the pH is about 1.5. Alright, so we're going to swap this out for a buffer solution. Go ahead and rinse this off. With some, there's water. And we'll put this down in solution. Make sure we're acidic. So it looks like we're starting out at a pH of about 0, so we're definitely acidic enough. And that works. So now actually I'm going to adjust things so we can have a stir bar in solution. And we are going to add our sodium hydroxide to our large burette and start our titration. So I'm going to move things around a little bit to get the rest of that set up. Alright, so we've got this set up here, we've got the stir plate under here, we've got our pH probe in. Now I'm going to add some of our sodium hydroxide solution. In our burette, we've got 50 milliliters here. So now I'm going to go ahead and turn on the stir bar. And I'm going to add that dropwise, so that way I can record these values while we're actually adding.
The last couple minutes of this video are showing the titration.
where we're adding dropwise to our solution and the pH is gradually increasing. So we actually started out below 0 for the pH, so it's just above 0 now. And as you watch this, you're going to actually see the pH slowly increase up until we do not have any more of the fully protonated amino acid glycine, and then you're going to see a rapid jump, and then you're going to see it level off again around a pH of 8 or 9 as it then slowly increases until the basicity of the solution maxes out. If you were in the lab, feel free to fast forward up until about 12 minutes and 30 seconds, and that's when I'll start talking about actually graphing the data. Within the experimental supplements folder, there is an Excel file that says glycine and unknown titration data. That is the Excel file that I'm going to be working on for the remainder of this video. You can also look at the PowerPoint, which is titration of amino acids, and that gives some details and example graphs of the titration of amino acids. At this point, we're at a pH of about 1.59. It's pretty clear that all of the excess hydrochloric acid is now protonated. So now in solution, the acid that we have, the strongest acid that we have, is the fully protonated glycine. So you can see the pH on the screen is slowly increasing from 1.5, and we're very close to about 2 right now. And now we're at 2.81, so I suspect there will be a very rapid jump. With another drop, we could be up to 3 to 4, and then another drop after that, we could jump up all the way to 8. And that means we've reached the point of, right now, since we're below 5.97, which is the PI of glycine, we have reached the point where all of our carboxylic acid functional group is deprotonated. So the PI value is the exact point, so once we reach a pH of 5.97, that means all of that carboxylic acid is fully deprotonated. This is a rapid jump over into Excel, but we're going to look at the details of what the expected graph would be, or what a perfect graph would be. So as you're taking the data, you might have recorded drops or milliliters. When I did this, I recorded milliliters, and I was lucky that my 0 equivalent mark was the point at which there was no excess hydrochloric acid in solution, and I had enough hydrochloric acid to fully protonate the amino acid. So looking at what we have here, we've got milliliters added. So that is a crucial data point you obtained in lab, as well as pH, which is another crucial data point you obtained in lab. So with these two values, you have enough that you could make a graph. However, with these graphs, the references you see, and specifically with that PowerPoint reference I mentioned, usually they give equivalents of the base that was added. So with glycine, when we have 0 equivalents of our sodium hydroxide base added, that means that we have our fully protonated amino acid. So with glycine, the R group would be hydrogen, which isn't an appropriate representation for an R group. But anyway, if this was glycine, this would be hydrogen. So specifically, our carboxylic acid and our amine are fully protonated at the 0 equivalent mark for this specific graph. The pKa1 value is a 50% equivalent of the protonated version and 50% equivalent of the deprotonated carboxylic acid. That is at 0.5 equivalents of sodium hydroxide being added. We have all of our protonated glycine, and we add 0.5 equivalents. So if we have 1 mole of our protonated glycine and we add 0.5 moles of sodium hydroxide base, we will deprotonate half of this to get this product, which means we're at 0.5 equivalents. So that is this mark right here on the graph. And that is also the pKa1 value, which is a pH of 2.34. So I can look at this graph and double check to see if we were going to add a line to this, would that line intersect 0.5 equivalents at the y value of 2.34? It looks like it's very close on this graph. Once we get to 1 equivalence of sodium hydroxide being added, now our amino acid is in its neutral form, which is referred to as the pi value. And at that point, when 1 equivalent of sodium hydroxide is being added, we should be at a pH value of 5.97. It looks like the intersect would be about right here, which, bringing that over to the y-axis, looks like it would be about 5.97. The pKa2 value is a 50% amount of the neutral form and 50% amount of the deprotonated amine, which is neutral. Once that's deprotonated, here it has a positive charge. Once we take one of those protons, it's now neutral. So we have our basic form. It's as basic as it's going to get. And once we have 50% of the neutral form and 50% of the basic form, that would be at 1.5 equivalents of sodium hydroxide being added. The pH value for that is known to be 9.6. It looks like that's probably just a little bit high on this graph. And then finally, once we reach 2 equivalents of base being added, we have fully deprotonated. So now all we have is this. I'd expect that we would see a little bit of jump after that, because now we're just adding straight sodium hydroxide to the solution. We're going to increase the pH a little bit. So that's why we see it jump one more time and then plateau off, because even when we add sodium hydroxide to this large volume of solution, it's probably not going to impact the pH all that much from there. All right, looking back here at how we actually graphed equivalents of sodium hydroxide within this graph so that we could relate it to more closely to the pKa values and acidic form, neutral form, and basic form, looking at equivalents of base being added. Once we have milliliters added, I have converted milliliters to millimoles right here in this equation. So I have my units above, and then I have the values below, because within Excel it can't calculate it. So if I would have said like 1 liter right here, it won't recognize that as a number. So that's why I put my units above and values below. So for milliliters of sodium hydroxide, we have 1 milliliter of sodium hydroxide, and I'm going to convert that to millimoles so that on my data table over here, I can multiply my number of milliliters by the number of millimoles of sodium hydroxide in every milliliter. So converting milliliter to liters, because I know the molarity, as this value was given in lab, it was on the container in lab of 0.9589, I'm going to take milliliters divided by 1,000, because there is 1 liter and 1,000 milliliters, and I want milliliters to cancel, so milliliters needs to be on the bottom. And then I'm going to multiply that by the number of moles per liter, and then multiply that by millimoles per mole, and that will get me the number of millimoles. So again, converting milliliters to millimoles, I'm going to multiply that by specifically just this, because this will cancel here. So liters per milliliter will cancel, and moles per millimoles will cancel, because we've got 1,000 on the bottom and 1,000 on the top. So calculating this, if you want to do the full calculation, you could take 1 divided by 1,000 multiplied by 0.9589 multiplied by 1,000 equals that. But since we're dividing by 1,000 here and multiplying by 1,000 here, that cancels, so you just need to take 1 multiplied by that, which will clearly give you that. So for millimoles, that's just going to be your milliliters times this molarity value, which is 0.9589. Graphing milliliters to pH would be better for sure than graphing drops to pH, and graphing millimoles would for sure be better than graphing milliliters, because millimoles has a direct reference in how our glycine is related to the base that we're adding. Graphing equivalents is a little bit easier to look at based on the specific reaction that we're looking at. But you'll see once we get to a little bit later in the experiment, we won't be able to do that. So either graphing millimoles to pH or equivalent sodium hydroxide to pH are good options. For the glycine that we used in this experiment to make this graph, now this is not the data that I want you to draw, this is just the intro, but for graphing this graph, 196.7 milligrams of glycine was used. We can convert milligrams to grams, and then using the molecular weight of glycine, convert grams to millimoles to figure out how many millimoles of glycine we actually have. And glycine and sodium hydroxide are at a 1-to-1 mole ratio. So when we calculate that, the number of millimoles is going to be 2.62. So again, 196.7 milligrams divided by 1,000 milligrams. To cancel out milligrams, it leaves us with grams. Grams multiplied by 1 mole over 75.07 grams will get us moles. And then once we multiply that by 1,000 millimoles, that will get us millimoles, and that is the value there. So for the equivalence of sodium hydroxide, I'm going to take the millimoles and divide that by 2.62, because that's how many millimoles of glycine we have, and since sodium hydroxide and glycine are at a 1-to-1 mole ratio, that is how many equivalents of sodium hydroxide we would need to add. And finally, for the last piece of data, once we have the number of millimole equivalents of our sodium hydroxide base, we also know that that's at a 1-to-1 ratio with our glycine, so we can calculate the molecular weight of glycine based on our data. So for the 2.62 here, this was calculated, but when you're actually doing this in the experiment, you're going to look at your actual data on your plot. So if we go from 0 to 1 equivalence, so 0 to 1, which is between the 2.59 and 2.8, let's say it's 2.62, that is the number of millimoles, or then you can convert that to moles to calculate the molecular weight of the compound we're assessing. So again, when we're starting at 0 and going to 1 here for our equivalent sodium hydroxide, we can say that 2.62 millimoles is the amount. Now, if I was actually guessing this, it looks like it might be a little bit closer to like 2.75, but based on what we know, it is 2.62 because that's how you can calculate the molecular weight of glycine. So experimentally, I would say 0.00275 is my number of moles. My number of grams is how much we weighed, which is 0.1967. So you take 0.1967 divided by the number of moles, and that's in units of grams per mole. So that's assessing the molecular weight of the compound, which in this case, since we know the data and it matches up pretty close based on our experimental data, we assess that to be the molecular weight of glycine, which is 75.08 grams per mole. Now let's move to the experimental data. So this is the experimental data that I want you to use. So everything on sheet 1 that we looked at, your actually Excel file is going to look a little bit different. So yours is going to say glycine. I want you to analyze glycine for sure. So when you analyze glycine, you already have this data. So the number of drops of your sodium hydroxide and the pH of your resulting mixture is the data set that you're going to use. So this is what I want you to look at. And then for the amount of glycine that was taken, let's say we started with 208 milligrams or 0.208 grams. And then again, for our sodium hydroxide solution, that was 0.9589 molar is the molarity of the sodium hydroxide solution. So when calculating this, we want to convert drops to milliliters. There are 18 milliliters in a drop. So I'm going to say this equals this A2 divided by 18, which 0 drops is 0 milliliters. Let's make sure that matches up correctly. So 4 drops is 0.22 milliliters. That sounds about right. And it looks like between 16 and 20 drops is, so 18 drops is 1 milliliter. So it looks like our calculation's right. So I'm actually going to, so again, once I calculated this, this was A2, so the number of drops divided by 18, because there are 18 drops per milliliter, and then I'm going to just drag this all the way down. Now when I drag it, you could drag it like this, but this will just highlight all the cells. If you drag starting from the middle, you need to start from the corner and drag it down, and that will give appropriate calculations for everything here. Like I said, milliliter is not the best calculation for sure, so we want to convert that into moles or millimoles. Since we're using such dilute solutions, it makes a little bit more sense to do millimoles. And we saw previously that what we need to do is take the number of milliliters and multiply that by the molarity of our actual base solution. So in this case, we're going to take, again, milliliters, multiply that by molarities. That'll give us the number of millimoles, and we're going to leave these two variables out. And again, when calculating this, we would just take 1 divided by 1,000, multiplied by 0.9589, multiplied by 1,000 equals that. And that's what I have shown right up here. So we've got A40, so that is 1. And then we've got divided by B41, which is this, multiplied by C40, which is that, multiplied by D40 equals this. So when I calculated this, I basically just said, I'll just do it over again. So this equals 1, and then I'm saying divided by 1,000 multiplied by the molarity and multiplied by the number of millimoles per mole, and then when I press enter, that does the calculation for number of millimoles. Now I know that I don't need to calculate all that, so I'm just going to multiply by 0.9589 to convert from milliliters to millimoles. So this equals my number of milliliters times 0.9589. And then I can drag this down again to calculate all of these values. And then finally, for the calculation of equivalence sodium hydroxide, we can take our number of millimoles and divide it by what we calculate for our number of millimoles of glycine. So if we have 208 milligrams, we're going to divide that by 1,000 because we have 1 gram per milligram. So equals 208 divided by 1,000 divided by the molecular weight, and then multiplied by 1,000, and that equals 2.77. So we are going to take millimoles and divide that by 2.77. to get us our equivalent sodium hydroxide. And hopefully it matches up, and hopefully we get about 1 around the equivalence point, which we'll talk about that in a little bit more detail in a minute. It's not super close. It looks like it's quite a bit over, actually. It looks like our 1 equivalent is at 8.04, but like I said, we'll talk about that in a second. But now we have the data that we need to actually graph this. So I'm going to highlight the columns that I want to graph, and then I am going to go up to insert, and under charts I'm going to insert a scatter plot, which is that, and that looks pretty good there. There's no other data assessment that I need down here, so I'm actually going to drag this down closer to our calculations right there. Okay, so now we have our chart title, so we'll go ahead and name this, and this is our glycine titration, and we've got pH here, so I'm going to say plus, and then I want axis titles on here. So this is the pH, and this is the, in this case we graphed equivalence of sodium hydroxide added, Now notice that when I graph this, like I said, when I was analyzing this, our one equivalent of base being added was at a pH of 8.04, so that's pretty high. We actually expect this to actually be closer to 1. So this point right here at 5.97 should actually be closer to 1. So what happened in this case is that we actually didn't start recording values early enough. Or actually better said, we didn't actually start at a low enough pH of the solution. So you can see the pH here is starting at 1.8. So that was not low enough to actually get us to the point of 0. So the 0 point is actually going to be more like off of this chart completely. And then looking at it here, so our one equivalence point is actually more like at 0.8. So if our one equivalent sodium hydroxide value is at 0.8, then that means that our zero equivalent point sodium hydroxide value would be -1 of that, so -0.2. More importantly, in looking at the data that we have, our two equivalence value is 0.8 plus 1. So if our one equivalence value is 0.8, our two equivalence value is 0.8 plus 1, so 1.8. And it looks like that matches up pretty well. So that jump is starting at about 1.8, and that's what we expect, that the difference between our two equivalence value and our one equivalence value is 1. So looking at our data then, we can look at that and assess the number of millimoles between our 1.8 equivalence value, which is between these two values here, and our 0.8 equivalence value, which is between these two values here. Also looking at this, you can see that our 5.97 pH is between those two. So visually looking at it, I can double check that and make sure my pH matches up with that as well. It looks a little bit closer to the 0.84, so I'll actually just go from 0.84 and then to, and I said 1.8, so 1.84. So 0.84 to 1.84, I said 0.8 to 1.8, but I'll do those instead because they're a little bit closer to the numbers that we're looking for our pH values. Now we can actually assess the number of millimoles. So for assessing the number of millimoles, we need to take our 0.511 minus 2.34. So for millimoles, let's just say that equals 0.511 minus 2.34. So it looks like that gets us 2.77 millimoles. And then if we have our 208 milligrams and we calculate this through, I'll just show that calculation through one more time. So 2.8 divided by 1,000 divided by 75.07 times 1,000, and then one more time I'll show that here. So this equals our number of milligrams. And then I could divide by 1,000 and multiply by 1,000, but those two are going to cancel. So I'm actually just going to divide by the molecular weight there, and that gets us 2.77 millimoles. So that looks really good. When we have 208 milligrams, we know that's the number of millimoles of glycine that we have. And looking at our equivalence of sodium hydroxide, that's exactly what we assessed for our equivalence of sodium hydroxide necessary to get from the one equivalence point to the two equivalence point, or the PI to the two equivalence point. We could also look then at our pKa1 and pKa2 values more closely, but it doesn't really matter which one you choose as long as you know how you're relating to your equivalence, how you're relating your equivalent sodium hydroxide to the number of millimoles of glycine. From this point, we can do a little bit more checking and now look at the molecular weight. So for the molecular weight, we know the number of grams that we had is 0.208, so 208 milligrams divided by 1,000 is 0.208. The number of millimoles, based on our calculation up here, looking at our two equivalence point and our PI value, was 2.77. So 2.77 millimoles divided by 1,000 is 0.00277 millimoles. So for this, if we take, I'll just calculate it again, if we take our grams divided by our number of moles, that is the molecular weight, in units of grams per mole, and so we get 75.09 grams per mole, which is very close to the known molecular weight of glycine, which is 75.07. So at this point, all this looks great. But there's a chance that when you assess it, your data is not going to be actually that clean. Now, fortunately, we know this is glycine, so we can talk about exactly what's off and how that relates to the number that it should be. And let's do an assessment here, because even though this all looks pretty good, this graph still is not perfect in terms of calculating the equivalent sodium hydroxide based on the data that we've graphed. So let's look at the pKa1 and pKa2 value. So the pKa1 value is when we have deprotonated 50% of this. So we have 50% of this and 50% of this. The pKa2 value is when we have deprotonated 50% of this, so we have 50% of this and 50% of this. Those are one equivalence point away. So that would be the 0.5 equivalence mark and the 1.5 equivalence mark. Now, for this, we know that we actually need to look at our pH values to assess where those really should be. So we could just go from, so the 0.5 equivalence mark minus 0.2, and then the 1.5 equivalence mark minus 0.2. So we could go from 0.3 to 1.3. So if we did that, if we went from 0.3 to 1.3, let's start below 1.3 here, and then, oh, sorry, 0.3 equivalents of sodium hydroxide. So 0.3, we're right on 0.3. If we go to 1.3, that's right there. Now, this is problematic already, because if we look at these values, 0.3 equivalence is actually that pH value is less than 2.34. Now, it's just one off, so it's not too bad, but this one looks quite a bit off. So we're looking at 2.34 for pKa1 and 9.6 for pKa2. So we're pretty far off of what those values should be. So it looks like if we want to be more accurate and look at the pH to make this assessment of what we should drag to where, then we should actually be looking at, so 2.34, that's very close, and then we'll go just below for our 9.6 value here, which is right there. And then looking at equivalent sodium hydroxide, so if we take 1.53, so we'll say 1.53 minus, and this one was 0.38, 0.384, so I'll leave it at that. That's actually 1.15 equivalents. So I would expect that our millimoles is going to be a little bit higher than 2.7, maybe a lot higher. We'll see what the numbers are. So if I drag this down again, and I am at 0.32 to 9.52 for my pHs, which is based on again, the pKa1 and pKa2 values there, which we know are one equivalence apart. Then when we take the millimoles, we have 4.26. So 4.26 minus and 2.32, 1.06, 1.06 equals. So that's actually 3.2. So that's quite a bit different than our 2.77. So let's just calculate then, if we actually did have 3.2 for our number of millimoles, that'd be 0.0032, and when we enter that in, that would actually get us a molecular weight of 65 grams per mole, which is less than the known molecular weight for glycine. So this is a graph where we know what the compound is, but we can definitely run into some issues. So looking at the unknown, those unknown issues compile a little bit more because we don't actually know what our unknown is. So you're really just making a solid guess based on all the data that you have, and I recommend showing and explaining the best calculation in detail. So for what I did in this case, it looked like the 2 equivalence value and the PI value matched up, that distance matched up with the numbers we expected for equivalent sodium hydroxide. Everything looked pretty good there. in terms of our calculations. If I would have gone from pKa1 to pKa2, in this case, based on the numbers that we got, based on the way that our Acumet reader was reading the pH, maybe that was a little bit off on one of those. Maybe our volume assessment was a little bit off on one of those, but we were a little bit off on our numbers. So I want a short explanation of things that don't match up all that well too. So in this case, that is the difference between pKa1 and pKa2. That's a little bit off from what was expected, and our starting point clearly was not 0, so the starting point really should have been about -2 for this graph. That sums up the glycine titration. So now we're going to move on to the unknown titration. So again, within the Excel file that I mentioned, I already told you where to find that. You can go to the next sheet. So just in case you're not super comfortable with Excel, I've got different sheets here. So when I was giving this presentation, I started with the basically a close to perfect glycine titration. And then I went to a glycine titration based on some lab data, which this is exactly what you're going to graph, and this is exactly what you're going to present as your data. So one thing to note, that 208 milligrams there, I think 196.7 is what was weighed out in lab. I want you to say 208 milligrams, and like this is your data that you're presenting if you complete the virtual experiment. So finally, we're going to go to sheet 4, which has the data for the unknown. All right, so I'm going to move a little bit more quickly through this than I did the last one. For the number of milliliters added, that equals this divided by 18. There are 18 drops per milliliter. I don't know why I keep hitting 9 there. So we'll hit enter after we do that and drag it down. And for the number of millimoles, that equals the number of milliliters. And we're going to divide that by the number of moles per liter of our base solution. So that is divided by 0.9589. And then drag that down. That all looks good. So that's my number of millimoles. Now for my equivalence value, I can't do that yet because I don't know the molecular weight of my unknown. So I'm going to go ahead and just graph millimoles to pH, and it might turn out that that's a little bit easier anyway. So once I graph this, I'll take us back up here. So we want to insert and insert a scatter plot. That looks pretty good there. I'll move it down here because we'll be down there anyway in a second. After inserting that scatter plot, we can go ahead and edit the title. So we'll call this unknown titration. And then specifically, we've got unknown number 3 here. So let's call it unknown compound number 3. And this is our titration curve. And then we can go ahead, once you select that, you can go ahead and add your axis titles again. So this one is pH, and this one, and it's important to add axis titles because this one's millimoles now instead of equivalents of our sodium hydroxide. All right, and then one other key point is that a couple other key points. First of all, for the unknowns that it could be, we're going to narrow it down to 5. So 5 different compounds for the unknown. So lysine, glutamic acid, aspartic acid, alanine, or arginine. And for the unknown, we got 0.184 grams of this. So 0.184 grams was the specific amount, so 184 milligrams of our unknown amino acids. So that's what the AA stands for. So for the amino acids that could be unknowns, I've gone ahead and gotten the molecular weight data for each of them. So for lysine, that's got the long chain with an amine at the end, 146.19 grams per mole. Glutamic acid and aspartic acid have a carboxylic acid functional group. Aspartic acid just has 1 less carbon in the chain. Alanine is very similar to glycine, except it has a methyl group as its R group. And arginine has an amide functional group at the terminal end of its R group. Looking at the pKa values, the pKa1 values are all for the carboxylic acid functional group, close to the amine on the original chain, so all of them have the same carboxylic acid functional group. The pKa2 is always the amine, and the pKaR is the R group. So notice that for alanine, we don't have a pKaR because it has a methyl group. It's not acidic enough to be deprotonated, so there is no pKaR. For lysine, we have the amine, which has a pretty high pKa value to be deprotonated. For the arginine, for the amide functional group, it's very unlikely that it is going to be deprotonated. It can be, but it has to be under super basic conditions. This might be somewhat easy to see if you graph it, as long as you have a strong enough base that's being added to get you well above that pKaR value. For glutamic acid and aspartic acid, it's not surprising that all these values are relatively similar, and the pKa value of the R group is going to be just a little bit higher than pKa1, and this is the second carboxylic acid, or the carboxylic acid on the R group. And then the Pi values are here as well. Now, looking at the graph in general, let me adjust this a little bit here. Okay, so looking at this graph, one thing to note is that if we have, so we can either have an acid as our R group or a base as our R group for our lysine, or nothing as our R group. A couple of things is, first of all, in order to fully deprotonate all the functional groups, if we have 3 functional groups, we need 3 equivalents of our sodium hydroxide. So for whether we have any of these 3, we need 3 equivalents of our sodium hydroxide instead of 2 to fully deprotonate all of our functional groups. So in this case, it's 2 carboxylic acids and an amine. In this case, it's 2 amines and a carboxylic acid. That means that our amount of base being added is going to have to be more than what it was for our glycine. Also, looking if we have an acidic amino acid, we expect the jump to actually be a lot higher. So the jump is going to be at the 2 equivalents added mark. So one more time, the big jump in pH is at the 2 equivalents added mark. The Pi value is going to be a little bit subtle. So that's not going to be a large jump, because note that the Pi value of 3.22 is right between pKa1 and pKaR. So 3.22 is right between the pKa1, so deprotonated the first carboxylic acid, and pKaR, deprotonating the second carboxylic acid. It's right between those 2 values. So you'd expect basically a long flat line on your tail end for that, where your Pi is. Now your 2 equivalents mark on the other end is going to be a large jump. So we see a large jump right here, which is probably about where our 2 equivalents mark. And the reason I can guess that by looking at this graph is because this seems to be a relatively small area where before we jump up and then flatline off. So I would say our 3 equivalents mark is about where we start to flatline off. So probably around this area here. On the other hand, for lysine, our big jump is after pKa1. So at our 1 equivalence mark is the big jump. The Pi value is between pKa2 and pKaR, which is on the higher end. So if this was lysine, I would expect it to be a little bit low here, jump at about 1 equivalence, and then basically have very minimal movement up here, and then finally it'll bump up at the end and then eventually flatline out. So those are the 2 easy things to look at, basically seeing that big jump. So for glutamic acid and aspartic acid, the big jump in pH comes at the 2 equivalence mark. For the basic amino acids, the big jump comes at the 1 equivalence mark. All right, so hopefully we agree that we've narrowed this down. It's probably glutamic acid or aspartic acid. We've got a very long range here. We've got the jump, and then clearly this is not a very large number of millimoles to get from our 2 equivalence point to our 3 equivalence point. I find that the easiest to look at is between the 2 equivalence point to the 3 equivalence point. Unfortunately, we don't have a value for our two equivalence mark. So we're not given like a PI for our two equivalence mark for these. So we really just have to guess it. And I would say guessing it, I'm going to say it's around a pH of about 7. That looks like it's about in the middle of that jump. So that pH of 7 looks like it is right at about 4 millimoles. So I'm going to say that my two equivalence mark, I'm going to say that my two equivalence mark is at 4 millimoles. And then for my three equivalence mark, it's a little bit difficult to tell because this is a fairly steep incline all the way. It definitely flatlines off starting at about 5.5. I'm going to say that it's probably run out of its last functional group, so that last amine is gone by about 5.4. So we'll say the three equivalence mark is 5.4. And then for a number of millimoles, it looks like that one equivalence mark would be 1.4 millimoles or 0.0014 moles. So when we plug that in, it looks like our molecular weight is 131.43, which is conveniently very close to aspartic acid. Now, I think that the guess on here for the three equivalence mark could really be plus or minus 0.2 on this. So let's say we did say that it was more like 5.1. I think even that would be reasonable. That means our difference would be 0.11. That means the molecular weight would be quite a bit higher there at 167. So with that, you'd be inclined to guess glutamic acid. So this really just gives you a ballpark area to look at. I think we need to look in a little bit more detail though. I'm going to keep this at 0.14 and let's just do a couple more assessments. So I'm going to cut this here, paste it there, and let's think about like our 0.5 equivalent mark and our 1 equivalent mark, and again, so 0.5 equivalence is your pKa1, and then your 1 equivalent mark is your PI value, and then 1.5 equivalence is pKa2, and 2.5 equivalents is pKa3. All right, so we don't really know where our zero mark is. We already said we've got 1.4 millimoles from our pKa1 and pKa2, but let's just look at our pH values. So for our 0.5 equivalents of aspartic acid, we are looking at a pKa of 1.88. So at 1.88, we've got somewhere between 1.8 and 2 millimoles, so we'll say 1.9 millimoles. And for our 1 equivalent mark, that happens to be the PI value for aspartic acid, we're looking at 2.77 is the pH there, so at 2.77, just above that, we'll say 2.81 millimoles for that, 2.81. And for pKa2, actually that's going to be pKaR here, pKaR there, and then this is going to be pKa2. For the pKaR value for aspartic acid, we're looking at 3.65 for the pH. So at 3.65, we're just under 3.4 millimoles. I'll say 3.4 millimoles, 3.4 millimoles, and we've got 4 millimoles there. And then for pKa2, that should be about 9.6 for aspartic acid. 9.57 is very close, so we should be about 4.6 millimoles for that. All right, and then going back and looking at the distance between these, so we already said 2 equivalents minus 1 equivalent is 1.4, and it looks like the distance from 2 equivalents to 2.5 is 0.6, meaning the distance from 3 equivalents to 2.5 equivalents is 0.8. It's not too far off. It's a little bit questionable, so if you're 100% confident in the 2.5 equivalents, you could say maybe it should be 5.2. We said if it was 5.1, that would increase our molecular weight calculation a little bit if this was 0.0012, so something to consider there. Overall, though, I don't think that's convincing to change my mind for aspartic acid yet. But it is an argument that maybe the molecular weight should be a little bit higher. And then for the 1.9 millimoles, so 0.5 equivalents to 1.5 equivalents, there it looks like we're up to 1.5 millimoles with that distance there. So 1.5 millimoles from our pKa1 to our pKaR, which that matches up a little bit on the higher end. So before I said, okay, so this is one of these might be a little bit lower, one of these might be a little bit higher. So overall, I'd say we're about the same for this. I'm not super confident in the 3 equivalent value, so maybe a little bit lower for this, so maybe more like 0.0012. But looking at our 0.5 to 1.5 equivalents, again, that's 1 equivalence in total there, that distance is 1.5. So, okay, maybe it's a little bit over this now, but I'm still pretty confident in the 0.0014. And then for the PI versus the 2 equivalent value, it looks like that is about 1.2. So that's a little bit on the lower end. So 1.2, so maybe this molecular weight should be a little bit higher based on that. We could look at this a little bit longer, but I think that's good enough. I would say we're ballpark about where we should be with. Now for your report, another thing that'd be good to do is go ahead and mark these places. So if you could use a writing application to write over this and specifically mark where your pKa1, pKa2, and pKaR values and then your 1, 2, and 3 equivalent marks are, that'd be great to, again, further your convincing argument or your guess for what your unknown is. I just basically want to see things typed out for your argument for what the unknown is, not just the data. So give a brief discussion, and then you can supplement that with some drawings on your graph and comparisons with the pKa values of what it's competing against. In this case, it's competing against glutamic acid. So maybe analyze it, assume it's glutamic acid, and make an argument for why it's not glutamic acid for this lab report.